Welcome to this video on multiplying radical expressions. Let's begin. We're going to be using the property that the square root of ab is equal to the square root of a times the square root of b, or conversely, that the square root of a times the square root of b is equal to the square root of ab. Remember, this is only true for non-negative values of a and b. Alright, let's look at the first example. So we have 2 times the cubed root of 18 times 6 times the cubed root of 15. So I want to draw your attention to the fact that all four of these things, the 2, the cubed root of 18, the 6, and the cubed root of 15, these are all attached through the same operation, and that operation is multiplication. And multiplication is commutative, right? A times b is equal to b times a. 2 times 3 is the same as 3 times 2. So in other words, the order in which I write these four things doesn't matter. Therefore, I can rearrange them to help me understand what to do. So I'm going to rewrite this as 2 times 6 times the cubed root of 18 times the cubed root of 15. Again, they're all attached through multiplication. So now, it's pretty obvious that I can just do 2 times 6, which is 12. Okay, then I'm going to use that property that I mentioned. Remember, I said that the square root of a times the square root of b is equal to the square root of ab. Now, at this point, you might be thinking, but wait a minute, I don't have a square root, I have a cubed root. Well, that's true. But actually, I can say that this is true for any n, where n is equal to 1, 2, 3, so on. N can be any root. So actually, I guess you would start it at the second root. 2, 3, and so on. Okay, so I can use this, for example, with the third root, right? The third root of a times the third root of b is equal to the third root of ab. I can use it with the fourth root, fifth root, so on and so forth. So that's what we're going to do. We're going to put the 18 and the 15 under a single radical. Now, at this point, you might be thinking, well, I should probably just multiply 18 and 15, right? That would then be the natural thing to do. However, I'm going to strongly suggest that you don't. And here's why. What we really want to do, right, is we want to find pairs of three numbers, sets of three numbers under the radical that we can pull out. So instead of multiplying, we're actually going to divide. We're going to do prime factorization on both of these numbers. Okay? 15 is 3 times 5. So I'm going to rewrite this with a prime factorization of 18 times 15. So I have a 3, a 3, and a 3. So I'm going to put those all next to each other. Again, multiplication is commutative. Then we have a 2, and then we have a 5. Okay, do you see how that's so much faster and easier? Instead of getting whatever 18 times 15 is, some huge number that we then have to factor, if I just factor 18 and factor 15, I can it's a much faster way to see, oh look, there's 3 3s, I have a group of 3, one of those 3s escapes, so I have 12 times 3, and then of course the 2 and the 5 are trapped. 2 times 5 is 10. So this becomes 12 times 3 is 36. So I have 36 times the cubed root of 10. Okay? So again, resist the urge to multiply the values under the radical. Instead, factor them and then use that to simplify the radical. Alright, so think back about, back in a previous algebra class, how would you simplify 2 times the quantity x minus 5? Well, we had to use what is called the distributive property. So we'd have 2 times x is 2x, 2 times negative 5 is negative 10. So we're going to do the exact same thing here in example 2, although, as you can see, we have not just, a variable and some numbers, we have some radicals going on. So we're going to have 2 times the square root of 3 times 5 times the square root of 6 minus 2 square root of 3 times 2 times the square root of 8. Okay, so once again, I'm going to rearrange the furniture. So I'm going to write 2 times 5. I'm going to erase that because it looks like a decimal point. 2 times 5 times the square root of 3 times the square root of 6. And just for the sake of time, let's go ahead and stick both of those numbers under the same radical. Okay, then we have 2 times 2 times the square root of 3 times 8. Okay, again, resist the urge to multiply, guys. Instead, we're going to divide. We're going to factor out these numbers. Okay, so 2 times 5 is 10. That's pretty simple. 2 times 2 is 4. Okay, so we have 10 times the square root of 3 times 3 times 2. Right, that's our prime factorization. I just sort of reorganized them so that the numbers are next to each other that are the same. And here we have 3 times 2 times 2 times 2, 3 times 2 times 2 times 2. Okay, and remember to bring down your subtraction sign. Okay, so what's going to escape? Well, a pair of 3's escapes, and it looks like a pair of 2's is going to escape. So we have 10 times 3 times the square root of 2 minus 4 times 2 times the square root of 3 times 2. So I'm going to come up here because I'm out of room. 10 times 3 is 30. So I have 30 square roots of 2 minus 8 times the square root of 6. And that is my final answer. So let's look at another example. Once again, we need to use the distributive property to multiply this. So we will multiply those two terms and those two terms. So I'm going to have the square root of 3a times the square root of 27a squared. Then I have minus the square root of 3a times the square root of a. Okay? So the first thing I'm going to do is I'm going to put all of these under one radical. Again, not multiplying. It's a waste of time. Don't bother. So 3 times 27 times a squared. Right? Those all can be stuck under one radical. Minus 3 times a times a. Okay? Notice I didn't multiply anything. All right, let's do some factorization here. So we have 27 is 3 times 9, which is 3 times 3. Okay? So 3 times 3 times 3 times 3. Let's write out our a's. A times a times a. Okay, then we have the square root of 3 times a times a. All right, so since we're taking square roots, we're looking for sets of 2. So I have 1, 2, 3 sets of 2 over here, and I have a set of 2 over here. So 1, 2 3's and an a are going to escape. So I'm going to have 3 times a, and notice I still have a square root of a left over under the radical. Okay, over here, 1a escapes, so I have an a out here, and then the 3 is still trapped underneath. So when I go to simplify this, 3 times a is 9a. So I have 9a times the square root of a minus a times the square root of 3. That is my final answer. Okay, what if we have something like this, where we have x minus 2 times the quantity x minus 5? So there's two ways that I teach this. One is FOIL. If you remember your FOIL, it stands for first, outer, inner, and last. Okay, so first means I multiply x times x. X times x is x squared. Outer means the terms that are on the outside, so I have x times negative 5, which is minus 5x. Okay, then I do my inner terms. Negative 2 times x is negative 2x. Then I do my last terms, and my last terms are negative 2 times negative 5, which gives me positive 10. Okay, so that is the FOIL method, first, outer, inner, last. Then our middle terms are like terms, which can be combined. So that's x squared minus 7x plus 10. Okay, sometimes students don't like that method. Another way to think about it, or another way to do it, is to rewrite it as x times this whole thing. So you could have x times the quantity x minus 5, and then you have a minus 2 times x minus 5. Okay, then what we would have to do is we would have to use our distributive property twice. Okay, and of course we would still get the same answer. Okay, so you can use either of those methods. They're both doing exactly the same thing. They're just different ways of sort of thinking about it or writing it. And as you can see, both of them result in the same exact answer. So that is a review of how to multiply together two binomials. So we're going to do the exact same thing here, only as you can see, our radicals are back. So let's use FOIL. So here are our first terms. So I'm going to have 2 times the square root of 5 times 7 times the square root of 2. That's just my first term. Okay, then we have our outer terms. So our outer terms are going to be 2 square roots of 5 times 8 times the square root of 7. Okay, then we have our inner terms. Our inner terms are minus 3 square roots of 6 times 7 times the square root of 2. Okay, last but not least, we have our last terms, and as you can see, I'm sort of running out of room here, so I might have to write it sort of on the bottom, on the below a little bit. So I have minus 3 square roots of 6 times 8 square roots of 7. All right, so let's start simplifying this. So I'm going to rewrite this. So I have 2 times 7 times the square root of 5 times the square root of 2. Then I have 2 times 8 times the square root of 5 times the square root of 7. Then I have 3 times 7 times the square root of 6 times the square root of 2. Then I have 3 times 8 times the square root of 6 times the square root of 7. 2 times 7 is 14, and I can put 5 and 2 under the same radical. 5 times 2 is 10. So this whole term gives me 14 times the square root of 10. Likewise, this gives me 16 times the square root of 5 times 7, which is 35. So this whole term gives me 16 square root of 35. This gives me minus 21 times the square root of 12. This gives me 24 times the square root of 42. Okay, so let's think about if there's anything else I can do to simplify this. Can you see anything or think of anything that we need to do? Well, the one thing that I see is that there is one perfect square hiding somewhere. Can you find which of the 4 terms has the perfect square? If you said 12, that is correct. If you think about 12, we have 4 times 3, and 4 is 2 times 2. So this term is the only one that we can simplify. If you don't believe me, I can show you the rest of them. For example, 5 and 2 are both prime numbers. 5 and 7 are both prime numbers. 6 is not a prime number, but it factors out to 2 and 3. So 2 times 3 times 7, you can see there's no double numbers there. Okay, so the only one that we have to mess with, the only one we have to bother with, is this guy right here. Okay, let me rewrite this guy. 24 square root of 42. Okay, so I can rewrite the square root of 12. So let's just do that on a separate paper. So the square root of 12 is equal to the square root of 4 times the square root of 3, which is equal to 2 times the square root of 3. So going back to our problem, I'm just going to rewrite the square root of 12 as the square root, as 2 times the square root of 3. So let's write our whole answer. We have 14 times the square root of 10 plus 16 square root of 35 minus 2, and remember this is what we're trying to change here, the square root of 12, and we said that the square root of 12 is actually 2 times the square root of 3. So I'm going to write, I'll put it in a different color to bring attention to it. I'm going to rewrite this as 2 times the square root of 3, okay, minus 24 times the square root of 42. Okay, again, none of the other radicals can be simplified, unfortunately. So our final answer is 14 times the square root of 10 plus 16 times the square root of 35 minus 4 times the square root of 3 minus 24 times the square root of 42. Okay, so let's take a minute and reflect. If I had left my answer like this with the square root of 12, would you get full credit? And the answer is no. Okay, so anytime you have an answer with radicals, you always want to think about or look at a prime factorization of those radicals and make sure there aren't any perfect squares hiding inside those numbers. Okay, let's look at example 5. So again, we are foiling, we are multiplying. So we have the square root of 5 times 4 square roots of 10, so that's our first term. Okay, then we have our outer terms. So our outer terms are square root of 5 times 6 square roots of 6. Okay, then we have our inner terms. So our inner terms are negative 2 square roots of 3 times 4 square roots of 10. And then our last terms are negative 2 square root of 3 times 6 times the square root of 6. All right, so let's simplify this. So I'm going to have 4 times the square root of 5 times 10 plus 6 times the square root of 5 times 6 minus 2 times 4 times the square root of 3 times 10 minus 2 times 6 times the square root of 3 times 6. Okay. So again, your natural inclination is probably to do this multiplication, right? To multiply all these numbers. Okay, you can do that. I'm not your boss. I'm not going to stop you. I would, however, recommend against it. Instead of multiplying, I'm actually going to divide. I'm going to do a prime factorization. So let's see what that gets us. Okay, so the prime factorization here is 5 times 5 times 2. That's important because guess what? That means that I have a pair of 5s and that one of those 5s can escape outside of the radical. Okay, so that's why I do it this way. All right, what about the next one? I have 5 times 2 times 3. Do you see any repeated numbers? I don't. So I'm just going to be lazy. I'm going to do 5 times 2 times 3 or 5 times 6, and that's just going to give me 30. Okay, so since none of these numbers are the same as any of the other ones under the radical, there's nothing I can do. I can't simplify the square root of 30 in any way. Okay, so then we have 2 times 4. 2 times 4 is 8. Okay, again, I'm looking at 3 times 2 times 5. 3 times 2 times 5 is 30. Again, we just said there's nothing that you can pull out. There aren't any perfect squares hiding inside of the number 30. Okay, lastly, we have 2 times 6. That is 12. Okay, then the prime factorization here is 3 times 2 times 3. So let's write that out. 3 times 3 times 2. Right, so this time we do have a repeated number that can pop out. All right, so let's keep going. So we're going to have 4 times 5 times the square root of 2 plus 6 square root of 30 minus 8 square roots of 30 minus 12 times 3 times the square root of 2. So this becomes 20 square roots of 2. Let's combine these like terms. Did you notice the middle terms can be combined? 6 minus 8 is negative 2. So I'm going to have minus 2 square roots of 30. Then I have 12 times 3. 12 times 3 is 36. Pause the video and think about if you see anything else that can be done. Did you notice that these are also like terms? What's 20 minus 36? Well, 20 minus 36 is negative 16. So I can combine those and get negative 16 square roots of 2 minus 2 square roots of 30. So this is my final answer. You might wonder, is there anything I could do, or do you want to factor out? I suppose if you wanted to, you could factor out at negative 2, and you'd have negative 2 times the quantity, 8 square roots of 2, plus the square root of 30. But to me, that's a little bit extra. That's beyond the scope of what we really need to do. But if anyone did that, I would still give full credit for that. Okay, example 6. Once again, we are back to FOIL land. So let's get started. Our first term is 4 square roots of x times the square root of x. Okay, our outer terms, that's going to give us 4 square roots of x times 3 times the square root of y. Okay, then we do our inner terms. Our inner terms are 3 square roots of y times the square root of x. Okay, then we do our last terms. Okay, and it looks like that's plus 3 square root y times negative 3 square root y. All right, let's see if we can simplify this. So we have 4 times the square root of x squared plus 12 times the square root of xy plus 3 times the square root of xy. Notice that the y and the x are in different orders, but remember y times x is the same as x times y. And I want to write it like this so that it's obvious that these are like terms that can later be combined. Okay, then I have 3 times negative 3 times the square root of y times the square root of y. All right, well, let's see if we can simplify some of this. What is the square root of x squared? Well, the square root of x squared is just x. So I have 4x plus, again, remember we said that these two are like terms. So 12 times the square root of xy plus 3 times the square root of xy. 12 plus 3 is 15. So we have 15 times the square root of xy. Then 3 times negative 3 is negative 9. The square root of y times the square root of y, of course, is just the square root of y squared, which is y. So we have 9y here. Okay, if you don't believe me, I'll show you the intermediate steps. So negative 9 times the square root of y squared. Again, that's going to give you negative 9y. All right, so let's stare at this answer and make sure there are no more like terms that need to be combined. I do not believe there are, so I think we are done. All right, example 7. Again, we're doing some FOIL. So let's multiply our first terms. So we have 4 times the square root of 3x times the square root of 6. Then we have our outer terms. So our outer terms are going to be 4 square root of 3x times 2x times the square root of 3. Then we have our inner terms. So that's going to be negative 2 times the square root of 6. And then we have our last terms. So our last terms are going to be minus 2 times 2x square root 3. All right, so let's simplify this. So we have 4 times the square root of 3 times 6 times x. Notice I'm not multiplying 3 and 6 because what I really want, remember, I really want to do a prime factorization. I want to break it down, not build it up. Okay, then I have 4 times 2x times the square root of 3 times x. Then we have minus 2 square roots of 6. That's pretty unremarkable. Then we have 2 times 2x. That's going to be 4x times the square root of 3. All right, so let's keep going. So we're going to have 4 times the square root of 3 times 2x. Notice that this 3 is going to escape out of here. So we have 4 times 3 square roots of 2x, or simply 12 times the square root of 2x. Okay, let's keep going. 4 times 2x is 8x. Okay, again, this 3, right, there's a pair of 3's here. One of them escapes. So we have times 3 square root x. We can then multiply these together and we get 24x times the square root of x. Okay, then we just bring this guy down. There's not much to do here. And bring this guy down. There's not much to do here either. Okay. So let's write our answer all together so that we're not confused. So we have 12 times the square root of 2x plus 24x times the square root of x minus 2 times the square root of 6 minus 4x times the square root of 3. So if I look at my 4 radicals, are any of them like terms? Are any of them the same? I would argue that they are not. It looks like we've simplified everything as much as we possibly can, and I think now we're done. Okay, the last thing we need to talk about is how do we simplify x minus 2 quantity squared? So a lot of times people just want to write it as x squared minus 2 squared. However, please make this, write this in your notes. That is not correct. Okay, just like 3 squared is equal to 3 times itself, so x minus 2 quantity squared is equal to x minus 2 times itself. Okay, so anytime you see this, you have to rewrite it, and then of course when you have something like this, then we're back to FOIL. So be careful about that. So let's look at example 3. Again, we cannot just say that this is the square root of 2 quantity squared plus the square root of 3 quantity squared. Of course, that would be 2 plus 3, which is 5. Okay, I'm going to draw a big X through this. You cannot do that. Okay, you can do it, I guess, if you want to, but it's incorrect and it will not award you any credit. So be careful of falling into that trap. Okay, so what we need to do is we need to say, okay, well, anytime I square something, I'm multiplying that thing by itself. Okay, so that's what we're going to do. We're going to rewrite it like this. Cool. So let's go ahead and do our FOIL. So we have our first. So we have the square root of 2 times the square root of 2. We have our outer terms. So 2 times root 3. We have our inner terms, root 3 times root 2. And we have our last terms, root 3, root 3. All right. So the square root of 2 times the square root of 2 is 2. This is the square root of 6, square root of 6. And this is 3. Okay, so we can rearrange our terms. We have 2 plus 3 plus 1 square root of 6 plus 1 square root of 6 is 2 square roots of 6. So our final answer, 2 plus 3 plus 2 square roots of 6, we can add these together. We get, oops, that's a weird 5. 5 plus 2 times the square root of 6.